Welcome to Prep for Uni, online series of educational videos. In this episode, we explore one of the most fascinating phenomena in quantum physics, quantum tunneling. Quantum tunneling is notoriously difficult to grasp as it defies our classical intuition. To make it accessible, we'll use a vivid analogy: guerrilla soldiers breaking through a fortified defense line. Let's begin the journey. Welcome to the strange world of quantum mechanics, a realm where the familiar rules of classical physics no longer apply. In this story, we'll explore a remarkable phenomenon known as quantum tunneling, using the metaphor of guerrilla soldiers who appear where no one expects them. Just like shadowy fighters navigating dense jungles, quantum particles defy classical boundaries and find ways through barriers that should stop them. Let's follow these quantum guerrillas and uncover what makes their tactics so extraordinary. In classical physics, a particle is like a traditional soldier. When it confronts a barrier higher than its energy, it halts, much like a soldier stopped at a fortress wall without a ladder. There's no way over, under, or through it unless more energy is supplied. Classical rules are strict. No crossing means no passage. Quantum particles don't follow these rigid rules. They behave more like guerrilla fighters, elusive, unconventional, and unbound by classical tactics. These quantum guerrillas can vanish from one location and reappear beyond the barrier. It's not magic, it's the result of their wave-like nature, described by the quantum wave function. In the quantum world, a potential barrier is a region where energy is too high for the particle, at least classically. But quantum particles don't just bounce back. Their wave function extends into the barrier, meaning there's a non-zero chance of finding them in the so-called forbidden zone. Part of their probability seeps through, bending the rules of possibility. Inside the barrier, the wave function doesn't oscillate, it decays exponentially. Its amplitude shrinks with distance, but never fully disappears. This fading wave still carries meaning, a diminishing but real chance that the particle exists there or even beyond. This is the essence of quantum tunneling, a mathematical whisper of presence in the unlikeliest places. But the story doesn't end with the guerrilla simply appearing behind enemy lines. Once through, he rejoins his squad and moves forward as if the wall had never stood in his way. Similarly, a tunnel particle continues onward, its wave function now oscillating freely beyond the barrier. It resumes its mission, unfazed by the obstacle it just defied. Quantum tunneling isn't just a theoretical curiosity, it shapes our technology and our universe. It explains how alpha particles escape atomic nuclei in radioactive decay. It powers scanning tunneling microscopes, letting us visualize atoms. And it drives quantum diodes and tunneling transistors at the heart of modern electronics. In the classical world, barriers mean stop. But in the quantum world, there's always a glimmer of possibility. Probability flows where certainty used to reign, and the impossible becomes part reality. Our guerrilla metaphor reminds us, sometimes the most elusive agents and particles find their way through. In the classical world, barriers stop motion cold. But in the quantum world, even the impossible has a voice. With each shimmer of probability, nature shows us that paths we thought were closed might simply be hidden. In quantum mechanics, barriers don't always mean no entry, and the guerrilla spirit finds a way.